Supplemental math videos from Circle Christian School. Shapes and their similarity. They are proportional. All right, here's the big thing. It's apples to apples, oranges to oranges, big shape to small shape, big side to small side, big side to small side. It's all about the setup. A word about proportion. A ratio that equals another ratio, being compared to another ratio, is called a proportion. Proportions have to be equal in value. Okay, we're kind of used to that in the aspects of that we have quite often had to deal with fractions that equal an equivalent fraction. Now those fractions basically have what we call a scale factor to them. And that scale factor is that number that the numerator and the denominator are being both multiplied to make an equivalent equation. Okay, so we look at the 4 here and notice that if we multiply it by 4, we get the 16. Now for something to be proportionate, the denominator has to be multiplied by the same value, which this one is, and it gives us a 20. So we basically have a scale factor of 4. Scale factor is just the number that makes everything be equivalent, and factor, of course, means multiplication. Another way that we can check to see if two equations are equivalent to each other and are proportionate is that we can actually cross multiply over the equal sign. This is called doing the means over the extremes. So here what I'm going to do is take the 5 and multiply it to the 16, which would give us 80, which I would just put over here. And just ignore the little fence of equality at the moment. It'll show up in a minute and you'll understand. And I'm going to multiply the 20 to the 4 here, and it also equals 80. And because the two values are exactly alike, we know that the two fractions are proportionate. Okay, so going to the next problem, I also want to talk a little bit about those apples to apples and those oranges to oranges. Notice that the first fraction is a small fraction, and the second fraction is somewhat larger in the aspects of there are just more pieces to the pizza. And again, I like to generally put a small number at the top, a large number at the bottom. Does it really matter? No, not as long as you do the same thing to the other side here. That if the other side has a small number at top also, and then the large at the bottom, then we have a really good setup. And so we can look at different things to be able to figure out if the two equations are equivalent or proportionate. The first one is we can check our scale factor out and see if it's true. And if we multiply both the numerator and the denominator, the top and the bottom, I am speaking math geek speak, but you have to expect that out of math teachers. So we like to walk the talk. And that does make it true. We can also do the thing of cross multiplying to check and see if the two equations are also equivalent, which means they're proportionate, in this case by a scale factor of 4, by again cross multiplying. 25 times the 32 does give us 800, and 100 times the 8 does give us 800. All right, so we can also do either one of these. We can look for our scale factor on the next one here, where we have 6 over 14 equals 20 over 42, to see if the two equations are also equivalent and proportionate to each other. My favorite way is honestly just to do the cross multiplying thing, that if I have 14 times 20 would give me 280. And then we have 6 times the 42 would give me 124. 4, 25, 252. And note that the two are not equivalent to each other, so therefore we automatically know that the two are not proportionate to each other. I can also again check by scale factor on this that I really don't have anything that I can multiply the 6 by to get to the 20. I also just check down below to make sure, but if I take 14 and multiply it by 3, I do get the 42. Checking up top here, if we use that scale factor of 3, that we again see that it doesn't quite work. All right, so now we're going to work on some proportionate types of algebra equations. And again, note that you've got a small fraction and a little bit larger fraction happening here. A smaller number to a larger number. And I'm emphasizing this in this point because when I get to shapes, the setup here is going to be very important, and I do require the setup. So we're going to go and solve for x here, and we can either use a scale factor type of thing. 5 times what gets me real close to the 40? Great minds would say 8, so you could say that you have a scale factor here that equals 8. Another way we can write that is use the letter k equals 8. And up top here we'd go, what would we multiply to the 8 to get to the 16? And so we would know automatically here that x equals 2. Now the algebra way would tell us that what we're going to do is the cross multiplying. So I'm going to do a little fence of equality. I'm going to cross multiply, cross going up and then down. Your preference is to how you want to do this. There's nothing wrong with starting with the x, since that's the first thing you go to, and multiply down. Gives you a 40x. 5 times the 16 is 80. And you would divide out the 40 from both sides, or you could say 40 times what is 80? And all great geometry students would say 2. Same thing that we had before. All right, on the next one here, I'm going to do the same thing. Have my little fence of equality. I'm going to multiply down and multiply up. What you have to be very careful here is that when we multiply down here, that although this looks like x plus 3 times 5, and there's this great tendency to take the 3 and multiply it to the 5, what I like to do is I call this a hook. Sabrina has this little fish thing going on, so if you would like to see her way, totally bug her about it. She'll be happy to show you about her fish. But I do this little capturing of the one and hooking it down to the other, which means I get a 5 and it's being multiplied to an x plus 3. And then I'm going to hook the 4 here to the 9, and it's going to give me a 36. And now we can go ahead and solve. We're going to have to distribute before we move on. It's going to give us a 5x plus a 15 equals a 36. Going to minus 15 on both sides here. We get a 5x equals a 21, which now we're just going to divide by the 5 and divide by the 5. And so x equals 21 over 5. It's reduced as small as possible. Remember, all fractions have to be reduced, or we can change it into a mixed number or a decimal. Either one is perfectly fine, and we get 10 and 1/5, or you can do the decimal. Same thing happens on the next one, and I think I'm going to use blue here again. Fence of equality. Give yourself a little hook here. Go on down. Remember that it is 4 times x minus 5, not just 4 times x, equals the 3. And I'm going to go up here. Now, does that mean you can't go down the other way to do it? Certainly not, but what you have to be careful here is that it is not 3 times an x. It is actually 3 times the binomial here. Binomial means it has 2 terms. Nice little polynomial with 2 terms. So make sure that you write them together in parentheses. Oops, forgot my 1 there. And we're going to have to distribute again before we go and solve. See if you can do it before I can. Don't be afraid to draw your little arrows. 3x plus a 3. Very good. Let's see, I like to get my x by itself here, so I'm going to add a 20. Watch your signs. And add a 20. And so I'm going to get a 23 here, and a 3x equals the 4x. These say goodbye. Need a number here on this side, so I'm going to go minus 3x minus 3x. I know this is a little bit fast. If it's ever fast, just stop, take a look at it, run it back, see what you get. And we have x here equals 23. And of course, we can always George Poya it, put it back in, see if it makes a true statement. If I put a 23 back inside here, 23 take away 5 equals 18. So this would be 18 over 3. And we put a 23 inside here, which would give us a 24. And a 24 over 4. Let's see, this equals 6. Yes, this equals 6. And we're just as happy as a ladybug, snug in a rug. Moving on along to the next slide here, I'm going to talk a little bit more about similarity. Similarity between two shapes, between two polygons. They can be everything from a triangle to a triangle, a quadrilateral to a quadrilateral, a hexagon to a hexagon. But what happens with similarity is that there is this scale factor happening here, that all the angles stay the same, but what has happened is you either have a large or a small figure. I'm going to say that this started with a large figure, and then it reduced itself into a smaller figure, but it did it proportionately. That means every side had an equal scale factor between them. Now, to write this out, what we have is that quadrilateral A, B, C, D is similar to quadrilateral E, F, G, H. That results in the fact that angles are congruent, similar ones. So I have A congruent to E, B congruent to F, C congruent to G, and D congruent to H. But likewise, the angles tell us what sides are similar to each other. So if I'm going from A to B, and A was congruent to E, and B was congruent to F, then it is similar and has the same scale factor as going from E to F. And similarly, if I go from B to C, watching the angles here, I have 2, and I have 3, and down on the small one, 2 and 3, that BC is going to be similar, have the same scale factor as going from F to G, and C to D, and G to H, and D to A, and H to E. Make sure you keep similar letters with each other. If you started with D here, which has 4, and you're going to a 1, then on the smaller one, I have to go with H, that has 4 tick marks to it, and go to a 1 tick mark. Let's play apples to apples and oranges to oranges. You're given that triangle XYZ is similar to triangle MNO, and what you have to do is find side A here. Because they're similar, we know we have congruent angles, but we have a scale factor happening between the sides. All right, just going from left to right here, I see that I have a large triangle. This is how I'm going to do my setup. I do the large to the small shape, or it might be a small shape to a large shape. And it's proportional, so it's going to be a fraction equals a fraction. And there's always just kind of a small side, and then there's a large side. Can you put the large side on top and the small side on the bottom? Certainly. I'm just going to just kind of go small side to large side. It's just a matter of keeping your apples with your apples and your oranges with your oranges. Okay, and when I say that, apples to apples, oranges to oranges. All right, so let's match them up. My large triangle here, my small side is a 5. It is in between the angles that has a 1 tick mark and then a 3 tick mark. And then my larger side is 10, which is between the 1 tick mark and the 2 tick marks. All right, moving over to the smaller triangle, I am going to look for the small side, which is between the 1 tick mark and the 3 tick mark angles. So that's going to be 2.5. We're just matching them up. And again, I'm going to go to the large side, which matches up with the large side on the larger triangle between the 1 tick mark and the 2 tick marks on the angles. Okay, here's 1. That's my oranges. And there's the 2, which is going to be A. So now we have a fraction equals a fraction, and all we have to do is cross multiply. 10 times 2.5 is 25. Quick math says move that decimal over, equals 5A. We divide out the 5 on both sides, and we see A equals 5. Okay, so A over here equals 5. Now, another way that you can do this is by discovering the scale factor. For instance, two of the sides that we have is on my large triangle to my small triangle is the 5 to the 2.5, which is how I'd set up the ratio. Because I talked about big to the small, that's what I'm going to do. Remember, that's how the ratio comparison is. Whatever you talk about first goes up top, and whatever you talk about second goes down below on the bottom. So the scale factor here would be 5 over 2.5, which reduces down to 2. So we have a scale factor of 2 to 1. And if you really wanted to, you would go, oh, well, this is like, half as much. So the A is going to be half as much at 5. Another thing that happens inside triangles here have to do with parallel lines. And as you remember, that parallel lines, when they have a transversal, give us very cool angles. So right along here, I'm just going to kind of show you a bit of a transversal happening. Of course, each side of the triangle is actually a transversal to the parallel lines. So we have cool angles going on. And because we've got these cool angles going on, we also have some similarities happening. Now what's unique about these is instead of having two triangles side by side, what we end up with is two triangles, one inside of another. So right here what we have is a small triangle, and then we have a larger triangle, a small and a large. If you because we got these parallel lines and we have angles that all equal each other, we have a thing called the AAA similarity between two triangles. Angle, 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 similarity. Postulate. Okay? And we know these two triangles have same angles because they share a top up here. And because they share it, it's reflexive. They both have same angles. If they're same angles, they're similar. If they're similar, they're proportional. If they're proportional, then they have a scale factor between the two of them. So again, we can set up things apple to apple and oranges to oranges. And so I'm going to start with a small triangle. Always start with the shape up top. Setup is key here. Large triangle. And a fraction equals a fraction. You always have a small part and a larger part. This is your apples and your oranges, and a small part to a large part. Okay, so I'm going to start with my small one. The small side is 9 and the large side is 10. And then I'm going to move over to the large triangle and do the corresponding things. The small side, the 9 here is between the 2 ticks and the 1 tick, so the corresponding thing here is going to be the X, same thing. It's between a 2 and a 1 tick on the angles here. So that's the small, and it's going to be an X. And then we're going to do the large side. Now you got to be careful here because the larger side here is 10 of the small and 8 of what's left over, or 18. And so now we're just going to cross multiply to go and find it. And we end up with 10x equals 9 times the 8 is 72. Carry the 7 is 162. We're going to divide out the 10. Practice a little bit of your decimal stuff. If you divide a 10 out of anything, it's just moving the decimal over one place there, making it a little bit smaller. And we get 16.2. And you can find the scale factor from the small to the large, and it would be the same thing as the 9 over the 16.2. We just match them up. Or it would be the 10 over the 18. I think the 10 over the 18 might be a little easier to simplify, although you can just try it with your calculator. Would leave you with a 5 over 9. Let me make sure that 9 divided by 16.2 yields the same thing. 9 divided by 16.2. Math key, enter, enter, and lo and behold, it also equals 5 over 9. So we have a scale factor of 5 to 9. Moving along to the next triangle, this one just has 3 inside here. Similar things are going on. Because they're parallel, we got cool angles, corresponding angles here. The top one is, of course, congruent to itself. And so they're similar because of the AAA similarity postulate. So we can actually, in theory, take the small triangle, let it be similar to the medium triangle, which is, of course, going to be similar to the large triangle, and set up our 3 ratios here. And I'm still going to let this be small, bottom one be large, and then small and large. Oops. We have to go find A and B. So I definitely have all my information here for small, so I may as well start there to begin with and put the small to the medium one. Let's see, my small side's going to be 5, and then we have 35, and then then I'm going to do my medium one. My small side is A, and my medium, let's see, the large is going to be the 35 plus the 21, putting them together, which is what, 56. Very good. Alright, so now we're just going to cross multiply these together, and we get 35A equals 5 times 56, 5 times 6. Practice some mental math while you do this. Don't try to rely everything on the calculator. 5 times 6 is 30, carry the 3. 25 and 3 is 28. We're going to divide by a 35. And so A is going to equal, let's see, if we divide both of these by 5, 280 divided by 5 is 56. 35 is going to be 7. Is 7 and 8 actually 56? I believe it is. So A is going to equal 8. Awesome. Alright, now with that one down, we can actually set up the large one, and you can either set it to the small one here or the medium one because you have both. Your choice. But since I already have my small one here, I'm going to do 5 to 35, and the small side is going to be B, and the large side is everybody added together, 35, 21, and 4, which is 60. So we get 35B equals 300. And that means we're going to divide both sides by a 35. So B is going to equal, let's see, 150, 150 is, okay, hold on. Something that we can reduce, and we can divide everybody by a 5, which is going to give us 60 over 7, or 8 and what, 4/7? Yep. And so this one is 8 and 4/7, just a little bit larger. So you can find all the sides of a triangle just by using your A similarity. Apples to oranges.